As I mentioned earlier, these biometric systems are not perfect, so they have their own problems, and one of such problems is this thing called false acceptance problem or false acceptance rate. So the system sometimes still lets these intruders go through without getting detected, because the sensitivity of the system is fairly or relatively low. And it's also called false positive, because even if you're not the person identified as a valid user, the system still lets you go through the checkpoint. So that's one of the reasons why it's called false positive. So if I, for example, am an intruder and I claim to be somebody else, say Joe, and the system recognizes me as Joe and lets me go through the checkpoint, then we can consider it false positive. So we can also think of it in terms of a graph like this. So let's say the x-axis of the graph indicates the sensitivity of your biometric system, sensitivity of your biometric system, and then the y-axis of the graph indicates the error rate in terms of percentage. What's going to happen is, initially when the sensitivity is very low, your biometric system, its sensitivity is, when it's very low, of course you have tons of false positives. So it's not accurate. That's what we mean by a lot of false positives. So when it's not accurate, of course, you have tons of false positives, but as it becomes more accurate, of course, the error rate goes down because it's now more sensitive, and therefore you get less number of errors. So the next problem I'm going to talk about is called false rejection rate, or FRR, also called false negative. So what this is really the exact opposite of false positive. So when you are a valid user or a valid supplicant, the system still rejects you and say that you're not a valid user or supplicant. So if I draw a similar graph I drew earlier, right? So here, this one is sensitivity, and then the y-axis error rate in terms of percentage. When the system is not accurate, the accuracy is close to zero, of course the false rejection rate will be very low, because it's calibrated to detect basically much less than expected. So as time goes by, as actually the sensitivity of the system goes up, what happens is the system becomes more strict, and now even if you are a valid user or supplicant, it starts rejecting you. So that's why the graph actually looks like this. It goes up. So the error rate actually goes up because it applies more strict rules, and sometimes it gets too strict, and even if you are a valid user or supplicant, you still get rejected. So that's what false rejection rate is. So we talked about these two problems earlier. One was false positive or false acceptance rate, and then the other one was false rejection rate or false negative. And false positive, for example, is recognizing an invalid user as a valid user, which is a bad thing. So you want to have less probably false positives. And also false negative is, I told you, the opposite of false positive, where you recognize a valid user as an invalid user, so you want it to be also low. So the false negative rate, you want it to be low. But as we saw in the graphs, for example, the false positive, it was going this way, so that's false acceptance rate, right? That was the graph. And then the false rejection rate was going this way. So you cannot really have both of them in the same graph, but you can also see that they're going in two different directions. So the best you can do is somehow find the happy medium between the two graphs. So that is actually right here. So wherever these two graphs intersect, that point, I mean, the intersection point, those two graphs will be meeting no matter what, right? So that's actually one thing you can get out of this graph. But at the same time, the desired system you want, if you have that intersection point as low as possible, that's what you want. So for example, let's say this is the false acceptance rate and false rejection rate of a particular biometric system. So system 1, right? You can think of it this way. And then let's say you have another system that has its own false acceptance rate graph and then false rejection rate graph that looks like this. So let's say they meet here for system 2. So this is for system 2. And the thing is, as a whole, both false acceptance and false rejection, you want it to be as low as possible. So when you compare these two systems, for example, for system 1, if you go this way, right, the error rate is here when the sensitivity is this much, right? And in general, for the system 2, error rate is low when the sensitivity is there. So based on where the intersection is, you can actually make a conclusion of the overall performance of the system, because the system you want is wherever these graphs they meet, you want it to be as low as possible in terms of error rates. So the question I want to pose here is, out of these two graphs belonging to two different systems, which system is better, right? So you can think of that, and I'm going to come up with an answer after you spent a little bit of time. So I'm going to stop here.